Just a reminder, we've got homework number 9, MATLAB homework number 9 that are due this week. This is the last of the material, homework number 9. That is fair game for the exam. The exam is when? Next Wednesday, 1 week from tomorrow night. Okay, so look for an email before the end of this week. Similar deal to last time, right? So we'll have 3 total review sessions. One will be on a Sunday. We'll make sure the door is actually unlocked. What else?
Difficult to unlock.
Yeah, so we're going to talk to campus police, make sure we get the building unlocked. So I think we'll be good there. And procedures are going to be the same, right? So we can have make-up exams for those that have academic, professional commitments we know about ahead of time. Same procedure. You got to reply to the email. Make-up will be the next day in the dean's office. Everybody else got to be there on the Wednesday night exam, 8 to 10 p.m. And that's it. So 5 problems. Topics are sinusoids, systems, right? And then we've got derivatives for the rest of the 3. But the derivatives, it's going to be like derivatives in dynamics, right? Circuits. And we've got, beams. And essentially, one of those problems will be a sketching type problem where you will be using your knowledge of derivatives and slopes to look at sketching velocity acceleration kind of diagrams, current voltage, capacitor, inductor kind of diagrams, those things. Yes?
And the secret's not allowed?
Secret?
Well, I knew about something from AP Calculus, and my recitation teacher has hinted.
Yeah, so what he's getting at is actually we're going to cover material even between now and the exam that could actually help you. It's material not on derivatives, but material on integrals. If you've had more calculus and you understand integrals and you want to use more than just slopes to think about problems, that's okay. I mean, I can tell you the sketching problems, we grade whether or not the sketch is right. And if the sketch is wrong, the more work you show that is correct means you could get more partial credit. So we don't penalize people in here for demonstrating knowledge. Okay, that doesn't make a lot of sense to us. Okay, at the same time, we are designing problems for this next exam that if you've never seen an integral before, and doesn't matter, right? Everything we've covered up through derivatives is what we're testing on the next exam. If there's some things you know about integrals that are overlapping some of what we're going to introduce now and do next week, and you think some of that could help you on the next exam, more power to you. Okay? Definitely on the final exam, we won't make a distinction, We'll have sketching problems again. We'll say use your knowledge of derivatives and or integrals, whatever you want, right? Knowledge is knowledge to do the problems. Okay, good. So reminder on that. And also the old exam solutions I think I pulled up last time to show they're up there. Now is the time, right? I mean, the homework is due end of this week. If you get this homework done before Friday, then everything that's going to be tested, you've already done it. You can start working on crib sheet. You can block out a time. Best way to prepare, particularly if you didn't do well on the last exam, and you really want to make sure you move into the final on a solid footing, then if that's you, prepare now. It's Tuesday. Figure out how you're going to budget your time between now and like Sunday, and make sure like Sunday you've got a 2-hour block to sit down and do one of these exams. And then that still gives you Monday, Tuesday, Wednesday, right? All 3 review sessions to fix whatever needs to be fixed. Okay? And anybody that takes that approach can substantially improve where they are over the weekend compared to where they are Wednesday night during the exam. Okay? So it's up to you guys. Okay? And then my other final word of warning, if you did really well on the first exam, please keep in mind that 3 out of the 5 topics are pre-calculus topics. If you're good at math, have a strong math background. There was less new math there, some new applications, but less new math. So if you have more new math on this exam for you, it might mean you need to prep harder even if you did well on the first exam. Okay. Questions about that? 8 days. It's an eternity, okay, in the life of a college student. So ball's in your court. All right, so moving forward. I think I alluded to last time the idea that the next big piece of calculus after derivatives is integrals. Okay? And in this class, we make that connection from derivatives to integrals much more quickly than you would in a traditional calculus sequence. And again, you'll get the details of all this stuff if you haven't had it before. You'll get it again in the math department in Calc 1, Calc 2, Calc 3. Okay? But for us, we want to make this connection so we can go back and solve real engineering problems from courses in this building. Okay? And I think I made the point that if I think about all the calculus that we use in the engineering building, in the core classes, right, to derive the theory and really understand things, integrals pop up a whole lot more than even derivatives. Right? So integrals all over the place in core classes, in classes like dynamics and electric circuits and strength of materials, and everything beyond that. So good stuff, very powerful stuff, and really useful for physical problems. Okay? So integrals. Integrals in engineering. Okay, and like all problems that we do in this class, okay, we're going to see if we can't figure out what this is by means of physical example. Okay, and so here is true story. Okay, story from my own co-op experience. Okay, and what this is this is the truck entrance. Okay, at a company called DAP. Anybody know what DAP is?
No.
Anybody work in like home improvement over the summer? Do any painting or anything? Or DAP, they make things like, they make caulk, they make wallboard, spackling, stuff that you use for like painting and drywall and those kind of things, right? So they had some plants. They've got a world headquarters in Tip City. They had some plants also in the Dayton area. And what we would have is the world headquarters. As I was a co-op at the time as an undergrad engineering student, okay, and the world headquarters had a plant behind it, and the trucks would come with the delivery, right? And so we're talking about semis that would be filled with, skids of paint and caulk and raw materials, okay, and they would be bringing that back. And the problem is, if you're ever driving behind a semi and they want to make a right turn, right? There's usually a little sign on the back which says what? Yeah, wide right turns, be careful. In other words, they're going to swing way out left because when they go to make that right turn, the rear end pulls in close. So if you're in that right lane, you're going to get crushed by the truck. All right, and so that's fine with a long trailer, but you make this nice entrance to the corporate office and you've got landscaping and beautiful lawn and everything, and you can imagine what happens when the trucks miss the plant entrance. They come right into corporate headquarter entrance and they drag the back of the semi right across the manicured lawn. Okay, and so this only has to happen so many times when it's the corporate headquarters, right? So the bigwigs see this, they get upset and they say, can we get the co-op, please, to figure out how to fix this problem? Okay, and so essentially it's, can we widen the truck entrance in a way where we're not going to keep damaging the lawn? Okay, and so here's what the problem really looked like. Okay, I've got the truck entrance. It was on a main road actually here. Okay, and so let's just say that this is the entry here. So here's the main road, entrance over here to DAP. What they wanted to do is come in here and say, look, can we get the asphalt guys to come out and quote us what it would cost to kind of put this asphalt down here and add this extra region right here. And it needs to be pretty big because these are semis. So we're going to need like, say, 50 feet in this direction here and another 50 feet in this direction here. Okay, and the thing about asphalt is asphalt's not cheap. All right, and so to pave a parking lot like the one right outside of Russ, it's a number like in the millions to do a parking lot that size that takes hundreds of cars. Okay, and so it's really expensive stuff. You got to excavate everything out, clear it out first, and the material itself is really expensive. The labor is skilled labor. It's really expensive. Okay, and so the problem is they come in and they do this by the square foot when they give you an estimate. So how many square feet of asphalt are we going to put down? Okay, and so essentially what we want here is we want this arc that's really about a 50-foot radius here. Okay, and we want to have this new asphalt. Okay, but the asphalt contractor wants to come in here and just kind of eyeball it. Okay, so I'm going to come in here and I'm going to walk it. I'll have a wheel and stuff like that, right? But I'm going to walk it, and don't worry, I've been working in this area for a long time. I can give you a pretty accurate number. Okay, so if you're the asphalt contractor, you're going to under or overestimate the amount of asphalt it takes to do this job? I'm going to overestimate, right? And put in, oh yeah, it's going to take X amount of square yards, square feet, right? And so this is the problem. And so the guys at the corporate headquarters, they said, well, this is the reason we have co-ops, all right? Can I get the co-op to police this and go out? And can we maybe do a CAD drawing? Can we do something, calculate this area? Okay, and so now clearly me, being a mathematically minded co-op, I'm thinking, boy, there's got to be some calculus or something I can do here on this problem. Yes?
A formula of some type? Wait, no, that's not an option.
So let me walk you through it. Come on, can't you see I'm having fun telling this story?
Yeah.
Real life, guys, this is real life calculus, okay? And so the question is, you know, if I want to estimate this in a way where maybe the company, it's on their side, okay, as opposed to the asphalt contractors, right? Because that's my job, save money for the company. How could I estimate the area? Okay, so the co-op, you know, estimates the area with rectangles. Okay, so here's what I'm going to say. You know, what if I come in here and I say, well, let's just zoom in on one side, right? And so we're going to have to do both sides of this, but just looking at the area on one side. Okay, can I come in here and figure out, number one, you know, what's an equation for this curve right here? Okay, and so if I do that, I'll call this the y-axis and I'll call this the x-axis. Okay, and what I'd like to do is come in here and approximate this area in a way where I know I'm not paying for more asphalt than I'm going to get. Okay, and one way to do that is to come in and say, look, what if I come in with equal size rectangles, okay, where the area I'm going to use is an area determined like this. Okay, and so what's attractive to me, if I'm the company, is if I calculate it this way, okay, what I'm getting is I'm getting the area of all of these rectangles added up. Okay, and I would argue that this area is a conservative estimate, right? So I'm not going to get overcharged. Now, why do I make that statement? Say it louder.
There's a little bit above the rectangle.
Yeah, I'm missing these white pieces right here, right? I'm missing the white pieces. But nonetheless, it's a conservative way to kind of add that up. So let's think about how we could lay this out mathematically, right? So I know a couple things. I know that every one of these rectangles touches this curve. Okay, and so, you know, the beauty of this is calculating the area of a rectangle is not hard, right? If I got a rectangle, what's the area? Yes, length times the width. So in this case, maybe width times the height, right? And so if I had an equation for that curve right here, then isn't it true that every one of these points right here, you know, like this could be, say, x1, x2, all the way out to whatever, x sub n right here, right? Values of x. How would I get the height of the rectangle if I knew this function, y, as a function of x?
Well, the rectangle's areas first would have to be rounded up, but even if you did, there'd still be the underestimate.
Okay. So work with me here, right? So if I have these, let's say they're equally spaced, okay? And any one of these, you know, the width, I know what it is. It's the difference between these x values, right? So I'm going to start at 0, then I have x1, x2. Any one of these things, I can calculate the width, and it's just the change in x coordinate, right? So I'm going to call that delta x, right? The width of any one of these. Okay, and in fact, if this is the point 50 right here, okay, and this is the point 50 right there, and this is 0, okay, then if I had n rectangles, right, so in fact, let me even be clear. I'll write that here, with n rectangles. So n is the number that I use. It could be 5, it could be 10, it could be 100, whatever. What would the width of any rectangle be if I use n rectangles? Yeah, it's 50 divided by n, right? That's it. So I know what this is. It's, you know, how far I got to go and then divided by n. So if I want the height of any one of these rectangles, All right, and I know that each one of these rectangles is inscribed under this curve, right? In other words, it touches the curve right at the corner there. If I'm over here at x2, how would I get the height of the second rectangle?
Well, if you know the formula, you would figure out.
This?
Yes. Well, that's. I don't know this formula.
Okay, so we got to get the formula, but let's say I have a function f of x. How do I get the height of this rectangle if it's x2 here?
You plug in the value of x2 for f of x, and then
That's it.
the y value is.
Yeah, so the point is the y value, which is the height of any one of these rectangles, if I had a function for this, I could just evaluate the function at the x value and I'd have the height. So I'm coming up with a plan here, right? Because I got the width already, and if I could get the height, then I could get the area. And if I could do that for any rectangle, then how would I get the total? I'd add them all up. All right, and boss would be happy because when I showed him this picture, he'd know for sure that I was not paying for more asphalt than I need, right? Because my picture doesn't have the white space. Okay, so help me out here. If I've got this arc, 50 and 50 here, can I use like the equation for a circle to go here? Anybody recall what the equation of a circle is? It's on your algebra and geometry handout, by the way.
Circle's formula is
Yep.
x squared plus y squared, but that's not it, is it?
All right, so if the center of the circle is at the origin, then it's x squared plus y squared equals the radius squared. What if, in this case, is the center of the circle at the origin?
No.
No. So do you remember what is the formula for the equation of a circle that has a center? Let me ask you a leading question. Let's say the coordinate of the center is h comma k. Does it ring a bell?
It does for me.
Go ahead.
In parentheses, x plus h, and then squared.
You're getting warm. Somebody else?
It's much easier to write down than it is to say it.
Yeah, go ahead.
X minus h quantity squared plus y minus k quantity squared.
That is it. So she said it's x minus h quantity squared plus y minus k quantity squared equals the radius squared. So take a look at the picture. 50, 50. Where's the center of this thing?
50-50.
Yeah, it's right out here, right? Okay, and so I know what the h and k is. Okay, and so first of all, if I wrote the circle down, I would know that this is x minus 50 squared plus y minus 50 squared is equal to the radius squared. The radius is what? 50 squared, which gives me 2,500. Okay, so the equation of the circle looks like that. Is that this, y equals f of x?
Not yet.
So how do I turn it into this?
First, you have to put the x minus 50 on one side.
All right, so I got to solve for y, right? So this is the equation for the coordinates x and y that lie on a circle. I want this portion of the circle right here. I want to solve for the y value. So I think we can do this really in one step, right? If I move the x minus 50 to the other side, then I'll have y minus 50 squared over here. What do I have to do to get rid of the square? I take a square root, and then I'm still going to have y minus 50, so I got to get the 50 over here, right? So let me see if I can do this in one step. Okay, getting the 50 over here, this is minus. I'll get a positive 50 on the other side, right? Solving for y here. And then I have 2,500 minus x minus 50 quantity squared. It's all under a square root. When I take a square root, I get a plus or minus, right? So it is 2,500 minus x minus 50 squared, all underneath the square root.
Yeah, that's it.
And so the question is, which one of these is it? Is it plus or minus when I take that square root?
That's a tough one. But it's both of those will give you a value, and the smaller one has to be the right one.
Why is that? He said the smaller one has to be the right one.
Because it's much easier to draw this
Well, take a look. The drawing's up here, right? Okay, another leading question. If this value right here is y equals 50, then the rest of the y values on here are greater or less than 50. That's it, right? So this is 50. Do I add to 50 or subtract?
Subtract.
Okay, so I subtract. Bottom line is this is the lower part of the circle, right? The plus would give me a circle up here. Okay? So it's, yeah, so that's it. All right, so we got a plan now. Every rectangle has a width, delta x. Every rectangle has a height, f of x, where x is whatever one of these x values, right, along the axis here. Okay, so I ought to be able to approximate the area, okay, as follows. If I take this, okay, then I can get the approximate area, okay, by adding them up. So I'm going to write this as A is approximately equal to, okay, if I want to add up a whole bunch of things, is there a math symbol I can use for that? I use a big sigma, okay, so summation. That just means add them up, okay, and how many rectangles do I have? Do I have 50 rectangles?
I don't know. It never said.
I got n, right? I'm trying to do this general. I can use as many as I want here. I'm going to use n. So I got to take I equals 1 up to n. I got n rectangles. Okay, and I want to get now the area of every one, which is going to be what? The width, delta x, times the height. How do I get the height? The height's the y value, right? So I need the f evaluated at each point. I'm going to say f evaluated at xi. This is not multiplied. This is take the function, plug in the x value. That gives me the height. And then I'm going to have to multiply that by the width, right? Delta x. So that's the plan. So I think it's, you know, easiest to do this if you draw a picture with a real number of rectangles here. Yes?
What was the I again?
Yeah, so all this I is, it's like in MATLAB when you guys have written loops and things already, right? It's just a counter. So this is adding up from 1 to n. So for example, if I start at 1, I'll take the first x value, I'll get f of x1. I'll multiply by delta x, and I'll get a number. Then I'll make I equals 2. I'm going to put plus, then I'll do it again, f of x2 times delta x. So I've got all these x values, x1, x2. I'm going to add them up as I go. Okay, by the way, that's an example of a perfect question, right? Reached a point where I try to move forward, didn't see where I was. That's when you have to ask the question, okay? So kudos on that. F of xi times delta x. So let's plug in an actual number of rectangles, okay, and see what kind of numbers we get here. Okay, so for example, what if I use n is equal to 4? Okay, so I can draw this thing now with 4 rectangles. Okay, what would that look like? And so if I put n equals 4 on this exact same picture, okay, we'll draw the picture again right here. Okay, and so this is still 50. Right, this is still 50 here. The nice thing about 4 is I can get there by just bisecting. Right, and so this is 50, so I'll cut it in half, and then I will cut it in half again. Okay, and I got the function that comes down and goes about like that. Okay, so let's draw this thing and see what it looks like when n equals 4. Okay, here's the first rectangle like that. Okay, here's the second rectangle, which gets me halfway over there. Okay, then I got the third rectangle, gets me 3/4 of the way. And boy, this one looks kind of simple. How tall is the last rectangle? Yeah, the last rectangle is 0, right? Because it's the right end, right? This is the last point right here. It's the right end. So I've got these 4 points that kiss the curve, right? And each one of these is at a different height. Okay, by the way, do I know these x values right here? So let me write them down. This is x1, x2, x3. What's x4 going to be? Yeah, so I'll even write that here. x4 equals 50. Okay, so I think I can figure out the math on this, right? Each one of those x values, it's 50 divided by 4, right? So delta x, what's 50 divided by 4? 12.5. Is 12.5. So delta x, again, represents the width of any rectangle. Okay, so again, any one of these, all the same. This is delta x. Okay, so it's 12.5. Right, so then that means I've got each one of these x values. All right, and the area I'm going to actually compute is going to be just the crosshatched regions right here, right? Because I'm adding up the area of each of those rectangles. So this point right here, right, is the point, right, x1, f of x1, right? And so on. This is x2, f of x2, etc. So let's do the math. The area is supposed to be approximately, right, the sum of f of xi times delta x. I goes from 1 to 4 because I got 4 rectangles. So that means add them up. So just to be clear, the delta x is the same in every single one of these, right? So isn't this the same as delta x times the sum? I need f of x1 plus f of x2 plus f of x3 plus f of x4. Right? In other words, when I do this sum, every one of the heights gets multiplied by the same width. So to do this math, essentially what I need is I just need the f of x values, right? This is the point x1. This is the f of x value, the height of the rectangle. I need each one of those for x1, x2, x3, and x4. So we ought to be able to do that. In fact, you guys can help me out, right? The f of x value is what? It's this guy right here, right? So, for example, f of x1 is f evaluated at what point? 12.5, right? x1 is 12.5. So let me write out what we actually have here. Right? This is, I take this function f of x, I plug in 12.5. So I've got 50 minus square root 2,500 minus x minus 50. 12.5 minus 50 squared. Somebody run that on a calculator. F of 12.5. So this is 12.5. This is f of 12.5, right? Okay, that's that first point. So I'm sorry, you got what number? 16.928. Yeah, 16.93. That's what I got. Okay, and so similarly, right, I would do this for each one, right? Because f of x2, what's the x2 value? Yeah, it's halfway across, right? So it's 12.5 plus 12.5. So this x2 value is 25. So it's f of 25. If I plug in 25 into that equation, the number I got was 6.70. Right? If I want f of x3, this is f of what number? Yeah, x3 is 3 rectangles over, right? So it's 12.5 plus 12.5 plus 12.5. That's going to be 37.5. Okay, and when I evaluate this thing at 37.5, the number I get is 1.59. And do I actually have to evaluate f of x4 here? Right, it's 0. I can see that's where it kisses the axis. So it's f of 50. This is 0. Okay, and you can see that right here. Okay, so if I put in the 50 right here, I'd get 0. Square root of 2,500 is 50. 50 minus 50 is 0. All right, so I got the f values. Okay, and so apparently, if I want the answer, I'm going to take the delta x, right, and I'm just going to multiply it through. Okay, so back to here. So still for n equals 4, the area would be, we're going to take the delta x value. How much is delta x? It's 12.5 going to multiply by the sum of all those f values that I just calculated. So I've got, what, 16.93, plus I've got 6.70, plus I got 1.59, and then I got 0. Somebody want to run that? Did you multiply by 12.5? 315. I got 315.4. You got 0.25. Could be round off. I only kept 3 digits on those intermediate. 315.4 square feet, right? Because this is labeled right here in feet. All right, so this is what I do. I take this piece of paper and I take that number and I go out to the asphalt contractor and I say, so here you go. I'd like you to do this, and I'm going to pay you for 315.4 square feet of asphalt. And what's he going to say to me? All right, so my boss likes the bill, right? But the asphalt contractor doesn't like it because why? Right, because I'm missing all of the white spots right here, right? Okay, and so the thing is, okay, and this is pretty important, this underestimates, okay, the answer, right? And it's because I'm missing all of the white spots. Okay, and so the argument would be, you know, if I don't want to miss the white spots, how many rectangles do I need? Yeah, right? And in fact, this implies that you need an infinite number. Okay, I'm going to use this same sign here. Have I used that before? Infinity, the sideways 8. I need an infinite number of rectangles to get it right. Okay, and so that's the issue. And so I got some options. Now, you know, back when I was a co-op, it actually wasn't even that easy. You could do it, but it wasn't that easy to even approximate infinity numerically. Okay, could do it. And certainly, boy, it'd be hard to do right here on the board, right? We just did n equals 4. It took us about 10 minutes here to get through this for n equals 4. Okay, so boy, wouldn't it be nice if we had a way to approximate this thing with an infinite number of rectangles and get the right answer without a whole lot of computation. So here's the thing. Turns out that by definition, what I want here, okay, is I want the following. I want the true area, which is, I'm going to use a symbol we used with derivatives. This area is what we call a limit, okay? And the limit in this case is an infinite number of rectangles, so n approaches infinity, okay? And I need an infinite number of these added up, so it's I equals 1 to n, all right? So I'm going to do an infinite sum now, okay? And what I'm going to do is I'm going to take f of xi times delta x. Now, keep in mind, if I have an infinite number of rectangles, what's happening to delta x over here? That's the width of any rectangle, right? Yeah, so it's really the same statement, right? N approaches infinity is really the same thing as delta x goes to 0. Think about it that way also, okay? So skinny, skinny rectangles, as many as I can think up, I'm going to jam in there. Okay? And so it turns out, you know, that is the area. Turns out, by definition, this is what is called, okay, an integral. This symbol looks like a big S. And in fact, I'm going to put these two numbers on it. They're called limits. The limits from a to b, the integral from a to b. And when I do an infinite number, this f of xi just becomes the function f of x. Okay? And delta x going to 0 becomes dx. Okay? And so here's the statement. What I have just concluded that I need to do here, which is use an infinite number of rectangles. On the left side of the equation here, this business is the exact area, right, under f of x, okay? And it's between any 2 points, right? Between, say, x equals a and x equals b. In this case, for this problem, right, the a is 0 and the b is what? 50. Okay, so that would be the a and the b in this case. Okay, so that's the left side of the equation. The right side of the equation, okay, is what's called the definite integral of the function f of x, okay, from x equals a to x equals b. Okay? So apparently here what we have is a definition. Adding up an infinite number of rectangles, delta x approaches 0, n approaches infinity. Either way you want to think about it, it's the same thing. Adding up the area of an infinite number of rectangles, apparently by definition, is the same thing as evaluating this guy, what we call a definite integral of that function, small f, between the same two limits, a and b. Okay. Here's a key thing. If I want to evaluate that integral, turns out I need what's called the fundamental theorem of calculus, okay, which is as follows. Okay. The way I evaluate this integral, right, the definite integral from a to b of small f of x dx, okay, is equal to, when I integrate small f, I get a different function. I'm going to call it big F. However you're taking your notes here, whatever f you put here, make it look different than this one, okay? I'm calling this small f, I'm calling that big F. Okay, I get a different function, big F, and then I got to evaluate that function at the limits. And the notation used for this is square brackets with the a in the bottom and the b on the top on the right-hand side. Okay, and I want to emphasize this because this is made up by humans. Okay, it's just notation, but it is universal. Right? You evaluate an integral, it gives you an answer. Then I evaluate the answer at 2 points like this. It is big F evaluated at b minus big F evaluated at a. And here's the key. Big F and small f are related. Big F of x, okay, is what's called the antiderivative of small f of x. Okay. Somebody who's had calculus before, what's an antiderivative?
It is a function that when you take the derivative of, it gets the function you have.
It's the derivative backwards, right? Yeah. And the antiderivative is basically the derivative backwards. Okay, so turns out derivatives and integrals are connected. Not obvious why this is true. Okay, it is a fundamental theorem. That's how they're connected. Okay, if I want to calculate an area underneath a curve, the way that I do it is I evaluate the integral of the function under which I want the area. The way I evaluate the integral is I find the function that when I take the derivative of this function, I get the one here. Okay? And then whatever this function is, I evaluate it at 2 specific points. That's it. And I subtract the 2 numbers. Okay? And like magic, what that gives you is the area under the curve. Okay? So in order to do integrals, what you want, right, is you want to be able to find antiderivatives, do derivatives backwards, which is frankly the reason why doing this 3 weeks after we first said what a derivative was, actually makes a fair amount of sense. Right? We just figured out how to do all the derivatives forward. Can't we just take the same functions and just go backwards? Pretty straightforward, but that's it. If you can do that, then you can evaluate integrals. Okay? And another thing you're going to see as we move forward is many, many integrals we want to evaluate we can't do by hand anyway. Okay, so we got to do them numerically. We got to use whatever, MATLAB, something else, Ti-89, in real life many times. Okay, but there are an awful lot of integrals you can evaluate by hand. And back before computers, there were books you could buy, even the back of a calculus book, pages and pages of tables of integrals where people have figured out the derivatives backwards. Okay, and so it's neat, helps your problem solving skills. For us, we want to see how quickly can we get to some integrals we can use to solve some problems. So we're going to get back to this. We're going to do this problem using an integral the way we would do it from scratch if we knew integrals. Okay, but before we do that, we need to talk a little bit now about how to find these antiderivatives. Any questions before I move forward? All right, so we need the area in the curve. We need to do the integral. Need to find the antiderivative. So this is antidifferentiation. Antidifferentiation. Okay, here is the statement. Okay, if big F of x, okay, is the antiderivative of small f of x, which is what we're saying it is, okay, then this is what that means. Then small f of x is the derivative of big F of x. Okay, that's what the statement means. So I want to find the function big F that when I take its derivative, I get small f. Okay, so in other words, I want small f to be the derivative with respect to x of big F. So let's think about some that we already know how to do. Let's say that small f of x is the sine of x. Okay. Then what I would like is an antiderivative, big F of x, okay, which is the function that when I take its derivative, I get the sine. All right, so this antiderivative business, it requires that you have knowledge of derivatives. All right, if I know how to take derivatives, then I can do these things backwards. So maybe somebody that has never done an integral in their life before. Okay, would you like to take a crack at this based on the fact that we finished derivatives already? Okay. Somebody want to suggest to me what function, when I take its derivative, do I get a sine function? You've had calculus. Who hasn't had calculus wants to take a crack at this? Come on. Anybody? So we got the, go ahead. So the question was, all right, so this is brave, right? He doesn't even remember the question. He's ready. Okay, I love it. I love it. So sine of x, okay, I want to know, based on your knowledge of derivatives now, forget the new derivatives. What function, when I take its derivative, do I get a sine?
Oh, it's going to be the cosine.
It's a cosine, right? Yeah. Okay, now, when I take the derivative of the cosine, do I get the sine exactly, or is there anything else?
It's negative.
It's negative. So I'm going to need a negative. And remember, when we did derivatives, it was sine omega t. We're using an x, not a t. And do we have an omega here? The omega is just 1, okay? So it's simple that way. So the only thing is it's a negative, right? So what I'm going to need is I'm going to need minus the cosine of x, okay? And if you look at this, when I take the derivative of minus the cosine, right, I can check to see if this is right, right? Because the derivative of the cosine gives me negative sine, and because I have a negative, negative gives me positive. So here's a question for you. You can keep going if you want. You're doing good. Is this the only function that when I take its derivative, I get this?
Wait. Technically, can I say the answer?
Give me an example of a function. You know, what else could I have here besides a cosine?
Plus 6.
Plus what?
6.
Plus 6. I could put plus 6 over here.
Or plus 4.
I could put plus 4. I could put plus pi. I could put anything that when I take its derivative, I get 0, right? So in general, when I do derivatives backwards, I have to be a little careful because there's more than one answer, right? And the way we normally deal with that is we just say, hey, any constant, right? Any constant I can add to that. All right, so let's do another one. What if I said f of x is equal to x squared, right? Then again, this f, right, is supposed to be the derivative of the big F. What function, when I take its derivative, do I get x squared? It'd be x cubed, except when I take the derivative of x cubed, I got that 3, right? All right, so I got to divide by that, right? I need x cubed, but then the derivative there would bring a 3 down, so I got to have this divided by 3 now. Yeah, and again, I need this constant, plus c. All right, can we generalize that last one? Can we say, what if it's x to any power at all? Then the function that when I take its derivative, I get x to the n power. It needs to have one higher power, right? Because like if it was squared, it had to be 3. If this was cubed, it would have to be 4. Right? So I need another power here, so I can write this as x to the n plus 1. But what happens when I take that derivative? Yeah, this n plus 1 is going to come down now. And I don't have that here, so I probably have to divide by that, right? N plus 1 there. Right? Oh, and then I need the constant. I need this plus c on top of it. Okay? So this is true. All right, so that's how you do derivatives backwards, right? It requires a knowledge of derivatives. If you know your derivatives, then you can do your derivatives backwards, right? It's just the other side of the table. All right, so we're getting warm here. Now here's what I want you to realize. Based on this statement right here, right, the link between derivatives and integrals, fundamental theorem of calculus, when I integrate this guy, that integral is finding the antiderivative. That's the way you evaluate the integral. Okay? And so I want to emphasize here that the following statements are equivalent. Okay, so the statement is, number one, that if I have small f of x, right, being the derivative of big F of x, that's what I just said was what an antiderivative means. Small f is the derivative of big F. Okay, that is the exact same statement as saying that big F, okay, is the integral. Okay, and again, this symbol here, this integral sign, it looks like a large kind of S, right? And it's the integral, okay, of the function small f of x multiplied by dx. Those are the same exact two statements. Small f is the derivative of big F. Big F is the integral of small f. Same statement. Okay. Yes?
To clarify, d of x does not mean derivative. Right?
No, so this is the beauty of this, right? What dx literally means. It means the width, okay, of a rectangle whose width approaches 0. So it has physical dimension of width, but it's infinitely small, the number. Okay, and so that's a great question because the dx carries units on it, right? And so f of x, that's a y value, that's got units. Dx is a width, that's got units. When I multiply height times width, right, I get squared on the units, right? Like square feet, square meters. So yeah, the dx itself right there doesn't mean a derivative. It means an infinitesimally thin width, okay, in the x direction. All right, excellent. So, what's this statement then? If this is true, okay, so both of these guys mean that big F of x is the antiderivative of small f of x, okay? They mean the same thing. So here's the idea. If those two statements are the same thing, then doesn't it mean that what I just wrote down here are actually formulas for integrals? Right, so we can conclude just by looking at this, right? The conclusion is the integral of the sine of x dx is minus the cosine of x plus a constant. Okay, the integral of x to the n dx, right, is x to the n plus 1 divided by n plus 1 plus c. All right, so final point that I want to make about this, okay, final couple points. What is the difference between the integrals that I just drew on the board here and the integral sign that I drew up here? One's got limits, a and b. The other one doesn't. When I do an integral sign, okay, that has no limits on it, that type of integral is called indefinite integrals. Okay, and indefinite integrals means there's no limits, a and b. Okay, so no limits, a and b. Okay, and it's a much more important thing than just that. When I evaluate a definite integral, okay, so I've got functions here. They're functions of x, right? They could be equation of a circle, could be a sine function, an exponential, whatever. It's a function. When I find the antiderivative and I evaluate it at two numbers and I subtract the two numbers, when I'm done, what do I have? Do I have a function or do I have a number? I have a number. All right? A definite integral gives me a number. And the interpretation of that number is the area under the curve. And if that curve has units of length and length, then that area has units of area. But if that curve has voltage and current, then it has units of what? Power. Voltage times current. Right? So this idea of area, it means area under a curve. The axes on the curve could have any physical interpretation we want, right? And so when I evaluate a definite integral, I get a number, and the number's got physical units, and it's the area under whatever curve I'm integrating. On the other hand, when I do an indefinite integral, and I put a function in here, what do I get out the other end? A number or a function? I get a function out the other end. Okay, very important difference, right? An indefinite integral is simply the act of doing a derivative backwards. I get a function whose derivative gives me this function. It's a statement, right, that the derivative of this function, the slope of the tangent line to this function at every point, is equal to this function. That's the statement. It's not a number. It's a function. Okay? This one's a number. All right? So it's not just the issue of, do I have this plus c? By the way, good time to look at this. What happens if I put plus c inside these brackets and then I do this operation? Yeah, won't I get f of b, right? I mean, suppose my big F was this. I'd get minus cosine of b plus c. That would be this one. And when I did a, wouldn't I get minus cosine of a plus c? And when I subtracted it, what would happen to the c? It's gone. Okay, so this is another important point. When I do a definite integral, I don't worry about the c's when I do the antiderivatives. I don't need the c's if it's a definite integral. It subtracts right out of the evaluation. Okay? When I do an indefinite integral, if I don't have the plus c, the answer is incomplete. Right? I am missing possibilities. Anything that I can add that's a constant is also true. Okay? And so again, why is that the case?
Oh man, I just forgot.
Other than the fact that when I take the derivative of a constant is 0. Look, yeah, go ahead. Okay, so when I do the definite integral, the c would cancel out. With the indefinite integral, okay,
The C's still there.
the c is there. Why are there an infinite number of answers to something that when I take its derivative gives me this?
Any number that doesn't have an x on it is always has derivative of 0.
That's just an operational statement, right? Like when I take this derivative, I get 0. That's true. Let me ask you this. I take any function, say cosine of x, and I add c to it. And now I plot it again. What does it do to the curve? It shifts the whole curve up. What does that do to the slope of the tangent to the curve at any point?
Nothing.
Nothing. That's the reason there's an infinite number of answers, right, to an indefinite integral. The slope of the tangent to any one of these curves is the same, whether or not I shift it up and down by c. Okay? And because of that, when I do the derivative backwards, right, when I do the derivative here, I always get this, even if I shift the function around. Okay? All right, so what's the implication of this? Okay? What this means, based on what we just wrote, okay, is that derivatives in integrals are actually now inverse functions. Okay? That's the implication. Okay? And so from those same two things that I wrote, right, from number 1 and 2, okay, I can say that derivatives and integrals, okay, are, I'll call them inverse operations. What does an inverse operation mean? Go ahead. Yeah. Yeah. No, that's a good question. So he said, why do you always say plus c? Can't it be plus or minus c? So c could be anything, a positive or negative number, right? So you can, without loss of generality, you can always use plus and just say that c could be negative. Okay? Good? It's a good question. All right, so what does this mean to have an inverse operation? Like, for example, name me two functions that are inverses. Okay, tangent and inverse tangent, right? Inverse tangent means the angle whose tangent is. So if I take the tangent of the angle whose tangent is something, I get the what? That's what the inverse tangent is, right? So what's the other one? What's the inverse of the exponential function? The natural log, right? So if I take e to the ln of x, I get what? I get x, right? And if I take the ln of e to the x, I get what? Yeah, I mean, ln means the exponent I raise e to get whatever I'm taking the ln of. So the exponent I raise e to get e to the x is x. It's a who's buried in Grant Tomb question, right? That's how inverse functions work, right? They undo what the other one did, and you just end up at the beginning. Okay, so these two statements apparently is what we've got, right? Because look, if I just start with number 1, small f, right, is the derivative of big F, okay? This is number 1. What if I plug in the definition of big F? All right, in other words, this is the derivative. Big F, according to number 2, is the integral of small f. take a look at the statement. Small f is the derivative of the integral of small f. Right? That's back when I started, f of x. Or I could start with number 2. I could say big F of x, right, is the integral of small f of x dx. That's the statement number 2. And I could come in here for small f, and I could plug its definition. So isn't this the same as the integral of the derivative of big F of x dx? So look at the statement. Big F is the integral of the derivative of big F. The integral undoes the derivative, right? Okay, and so I'm back to big F. So inverse operations. I can use one to undo the other one. This is how you solve equations that have a derivative or integral on the other side. Right? I undo a derivative by integrating. I undo an integral by differentiating. Okay? All right. That's about the most math in one stretch you've ever seen in this class. Okay, so let's get back to the problem at hand, which is trying to figure out this area. Are there any kind of high-level questions here before we move ahead? Okay, and in fact, actually, this is a great time to pass out, I think, the summary sheet. So maybe we'll do that before we solve it. I got the summary sheet here for integrals, which is just like the sheet we handed out for derivatives. Okay, and just like we did for derivatives, we have also shamelessly pirated the inside cover of your calculus book. Okay, and so you'll see this exact sheet in your calculus book that is a sample of some tables of integrals, just to give you an idea that you can crank a lot of these out. But the front side is what's on the sheet. Okay. Okay, and I guess while that's going around, we'll go ahead and we'll recap it here.
You know what I realized?
Oops. Content. All right, so while that sheet's going around, let me just point out the key points to the sheet, okay, because we've tried to kind of bring it home in one piece of paper for you. All right, so the integral, all right, what we've just summarized in here, right, is that the definite integral between a and b of small f of x dx is the area under the function y equals f of x between any 2 points, x equals a, x equals b. What we would like to do is use this concept to solve this problem, right, where the area under the curve is the area of that asphalt, and in that case, the a is 0 and the b is 50. Okay, so we'll do that. Okay, and then what I have is I have the definition of how you evaluate that. Fundamental theorem of calculus that says to get that area, what I need is I need an antiderivative. All right, so that area is, I take the antiderivative of small f, I evaluate it at the limits, and I subtract the 2 numbers, big F of b minus big F of a. Okay, and so how do you do an antiderivative? You take the same exact functions that we had for derivatives, right, where we had the function on the left and the derivative on the right, and now we just go from the right back to the left. Okay, and that's all it is, right? So I'm using an x here because the context of our application is actually length, right? X in one direction, y in the other. But, you know, we dealt with sine omega t before. All right, now if I have sine omega x, right, the question is what function when I take its derivative do I get this? It's minus a cosine, but I need to divide by the omega. Now the beauty of this is if you just know your derivatives, right, you don't know any integrals, you can always check this because I can take this and I can take the derivative, right? So take the derivative here, minus 1 over omega out front. Derivative of cosine is minus omega times the sine. The omega cancels, the minus cancels. I get here, and the derivative of a constant is, of course, 0. So every one of these on the right, if I take the derivative, I get the one on the left. So again, if you're with us, if you know the derivatives forward, you can do the derivatives backwards. It's just going from right to left. So every one of these, same way. Cosine omega x now gives me 1 over omega sine omega x. Exponential function, e to the s times x. I get e to the s times x again, but I have to divide by s, all right? Because when I take the derivative, the s comes down and cancels it out. Here's the one we already had on the board, x to the n. X to the m plus 1 divided by m plus 1 plus a constant. This one, c times f of x. We talked about why this works for slopes. Who can tell me why this works for areas? Why is it that if a constant's out in front of a function, when I do the integral, thinking about the area under the curve, why does the constant stay out front?
I think it's the same reason why the constant stays outside when you take the derivative. But what is it?
Go ahead.
It's going to increase the magnitude of the area underneath the graph.
So literally the constant multiplies what? The width or the height of the rectangle? The height, right? Every rectangle that's being added up is c times as big now. So if I multiply every height by 2, then the area increases by 2, right? So it makes sense. The c stays out front. Okay, what about this? Adding two functions. When I integrate, apparently I'm stacking the areas. Does that make sense? It does, right? I mean, when you add two functions, that's essentially what you're doing, stacking them, right? Okay, so that makes sense. So great. All the same functions you're responsible for derivatives, you're now responsible for backwards, okay, for integrals. Anything beyond that, really, at some point you just, you got to use a MATLAB or got to use TI-89 or something. Okay, all the problems we have you do by hand in here are, subsets of these problems. Okay. Questions about the integral sheet? Pretty straightforward. Okay, so now that we have this tool, how can we use this to solve the asphalt problem?
Well, we do have y equals for this curve. We did before it's erased.
All right, so here's what we're going to do. We're going to go back to the asphalt problem, okay? And we already know that to find the area, what I want to do is do an integral. And we've already talked about how that's the same thing as an infinite number of rectangles and all of that. Okay, I'd like to work this integral problem the way that I myself would work an integral problem. Okay, and so here's what I would do. Okay, so back to the asphalt. In engineering, we are very much concerned in our classrooms about you understanding when you need to do an integral, okay? How to set an integral up correctly. We know that you got TI-89s and you got cell phones that can do integrals and MATLAB and everything else. We want you to understand where the integral comes from, why am I doing it, okay? And here's the idea. I want to find an area in the xy plane, all right? Here's y. Here's x, bounded between these two values, 50, 50, 0. Looks like this. Okay, and I know what the answer is here. This is y equals f of x, which was 50 minus, what was it? The square root 2500 minus x minus 50 squared. So I got the function. I want this area. Here's how I would do this. I'd walk up and say, well, I know I need to add up some rectangles. So let's draw one representative rectangle. Okay, and the one I'm going to draw is already infinitely thin. Okay, so this guy's located any value of x from the left, and the width of this rectangle is delta x, but I'm already saying it's infinitely small, so I'm just going to call this dx. Right? And if this is some distance x away, then I actually know the coordinate value here. This is coordinate x, and the height is just f of x, right? The x and y value is x and f of x. So what I really have here is I have an infinitesimal area, and I'm going to call that area dA, because it's infinitesimal. And what dA is, okay, is the width times the height. Right? So it's the height y times dx, right? Or again, y is f of x, so it's f of x dx. And so if I want to get the area, what do I do with all the dAs? I got to add them up. How many of them are there? Infinite. What does a summation symbol look like if there's an infinite number of things to add? I to infinity, and the shorthand for that is the integral sign, right? So whenever my summation is to infinity, right, if what I'm adding is infinitely small, right, then that is the operation of integrating. So I need the integral here of all the dAs. Just write it like that, right? And so in this case, that's the integral of y times dx, right? Y dx. And so now what we'll do is we'll put the function actually in there. So y is f of x. I need to get the integral of 50 minus the square root of 2500 minus x minus 50 squared dx. Now, when I evaluate this integral, am I looking for a function or am I looking for a number here? I want the area, right? I want this whole area by adding up all of these guys. So I need to have what on that integral? Limits. The first rectangle's here. And I stack them up as they move from the left to the right. So my limits are what? Yeah, 0 to 50. Okay, this is what we need you to be able to do in an engineering classroom, right? Look at, okay, what am I trying to calculate? How can I set up an integral to calculate that? It's very engineering-y, right? You draw it, okay? You sketch a rectangle. You get a sense for every rectangle. How tall is it? How wide is it? It could be any quantity. In this case, it's just the area under this curve, okay? But it could be any quantity that I want to add up, all right? So I set it up. So now I got to evaluate this. So now, even if you've had calculus in high school, okay, a year and a half of it, could you whip out a piece of paper and work this integral?
No.
It's not an easy integral to work.
Even with this, it's difficult.
Even with that, it's difficult, but it's doable. In fact, in the notes, we have the table of integrals answer for this for entertainment. Nobody uses tables of integrals anymore. Okay, we have computers. But the point is, look, it's the very first integral I'm ever asking you to evaluate. I can't do it by hand. It's a powerful statement, right? It doesn't mean the integral is not a powerful tool. I got ways to solve this thing. I can do some of this by hand. But at some point, I'm probably going to want to pull MATLAB out or something to finish it up. All right, so I got two different terms. Can I break this into two pieces? Mm-hmm. All right, let's do that. So the area is the first one. This is an important point. Everything in here is small f. It's all multiplied by the dx. So when I break this up, I need a dx on both terms, right? So 0 to 50 of 50 dx. And then I got this integral minus the integral from 0 to 50 of this guy, square root 2500 minus x minus 50 squared dx. Here's what I would argue. The one on the left I can do. The one on the right, I'm just going to call this I for now. I stands for the integral that I choose not to evaluate by hand, okay? Because it's too hard. Okay, it can be done, but it's a mess. All right, so how about this one on the left? Is 50 a special case of anything on the page here?
Actually, yes, it is.
Which one? It's just a constant, right? Can I use any of these formulas to integrate a constant? Well, so I'm doing the derivative backwards. So the question is, what kind of function, when I take its derivative, do I get a constant? And the answer is what? What kind of function has constant slope, right? Straight line. But look, I will point out, if you love formulas and you're just grasping at a formula for this one, x to the n will work, right? What's the n? 0. Isn't this 50 times x to the 0? So x to the n plus 1 is x to the first divided by 1. That'll work. Okay, so I can use the formula, but I can also use the knowledge of just derivative backwards. All right, and so let's go ahead and work that. So derivative backwards on this guy is, the first term, right? The integral from 0 to 50, right, of 50 times dx, right, is going to be 50 times x evaluated between the two limits. So the way you evaluate this, right, is you say 50 times the top limit, 50, minus 50 times the bottom limit, 0. Okay, so that is the big F evaluated at B minus big F evaluated at A. You evaluate it at the two limits. So what do you get? 2,500, right? This is 0. By the way, this is a formula way, right? I have small f is 50, big F is 50 times x. That's fine. Here's another way to think about it. What does the function 50 look like? Is this not the function 50 right here? And if I go from 0 to 50 right here, is not the integral supposed to be the area of this box? 50 times 50 is what? 2,500. Okay, so you can use formula, math. You could say, I know what it is. It's the area of a box. Okay, it's all the integral. That's just an aside. All right, so how about this guy? I need this I, right? So the area is 2,500. That's the first term right here. We just evaluated it, 2,500. And I got minus I, right, where the I is a mess. It's the integral from 0 to 50 of the square root 2,500 minus x minus 50 squared dx. Any suggestions for how to evaluate that?
Well, there is, if that was 2,500 plus x, that to minus 50 squared, that would have given me, yes, I can solve that, but no.
The minus is throwing you for a loop. So here's the thing. If you're really good at hand calculus, you can do these kind of forms. There's different kind of trig substitutions and things you can do, right, to work some of this out. But honestly, at some point, you got MATLAB for a reason, okay? And so to me, I'm coming in here and I'm saying, can I do this thing by hand with MATLAB? Now, MATLAB will do integrals a number of ways. It'll do numerical. It'll do symbolic. It's got a symbolic library where it'll try and find an analytical solution, not a numerical solution, that'll work for this. We're going to use that. To do symbolics in MATLAB, you got to tell it you're doing symbolics. And the way you do that is you say, hey, I'm going to use a symbolic variable x. Okay? And then, if I'm writing MATLAB and I don't know what to use for integral, what should I type? INT, sure. Right? Again, with MATLAB, if you're not sure what to do, pretend you're making it up yourself, okay, and just try it. Tends to work. So I'm going to integrate now the function, right? And so the function I've got is the square root of 2,500 minus the quantity x minus 50 squared. And I'm going to integrate that with respect to what variable? All right, so I got to tell it I'm integrating with respect to x. I put comma x. What are my limits? I'm going to go from 0 to 50. And I'm going to see if the symbolic toolbox here can do this for me. Oops. Integral square root of 2,500 minus x minus 50 squared. Oh, yeah, sorry. After the square root, there we go, x 0 comma 50. Try again. All right, so there it is. 625 pi. Exact number. All right.
There was actually another way to solve that thing. And it's a weird one.
All right, so hold up. We got 1 minute remaining. So we're almost there. Apparently the exact answer, okay? Apparently the exact answer is 2,500 minus 625 pi. Somebody want to run a calculator on that for me? So area equals 2,500 minus 625 pi. Give me a decimal. 536 point what? 5. All right, so square feet. Now, almost done. If I'm a college student and I've never seen an integral, and I see this on the board, and I see this, and the prof pulls up MATLAB and it spits that out like magic, I'm inclined to believe the prof because he's the dean and I believe what he says, okay? But it's a little unsatisfying to me. I mean, how do I know that that's right? And so I would ask you to take a look at this picture again and do this to it.
Oh.
You know, and is not the area that we just calculated a square minus what? This is a quarter of a circle, right? So isn't the area of the square 50 times 50, which is what? Minus a quarter circle, a quarter of pi r squared, right? Isn't r 50? So it's 2,500 pi. What's 2,500 divided by 4? 625. All right, you just spend an hour and a half doing a problem you could have done in 2 seconds. Okay? Welcome to engineering. All right, guys, so that's it for today. We'll pick up more next time.